Greetings to everyone. This is Akansha Bharti, student of Sri Venkateswara College of Engineering. Currently, I am in my 8th semester. Our today's topic is Design of Inverter Circuit for PV Power System, which is carried under the guidance of Mr. Murgesh PD, Assistant Professor of Department of Electrical and Electronics Engineering. My fellow groupmate is Deepthi A. These are the content of agenda today. Throughout the video, we'll go through each topic. Coming up to the abstract, the main purpose of this project is to design an inverter for PV power system with increased efficiency. The recommended architecture is achieved by coupling a typical boost converter with a single phase full bridge DC AC converter. Attribute of solar inverter are they offer just 5 active switches, and those switches can be driven synchronizingly by a variety of SPWM technique, where SPWM is sinusoidal pulse width modulation techniques. In lab prototype, simulation and experimental findings are eventually produced, and they will agree with theoretical analysis. Coming up to the introduction, as energy can be harnessed directly from the sun, solar energy is one of the promising renewable resources that used to produce electricity. The power generation of solar power system constantly varies in accordance with weather condition. Hence, the inverter play a crucial role. The variation of power production can have effect on grid power quality, including voltage swing, power factor change, frequency unsteadiness, boost in harmonic distortion, etc. The inverter function is to regulate power flow among grid sector in order to enhance generator productivity while awaiting unexpected conflict brought on transmission failure or generator instability. Inverters are essentially component of renewable PV power system. It convert DC power to AC electricity. They must able to handle PV system voltage and power rating. The stable and efficient operating of inverter depends on its control mechanism. A single stage boost DC-AC inverter is used to boost the output voltage. The inverter efficiency rise as more DC electricity is converted to AC. Single phase inverter are the most popular one that is in use. Coming up to the literature survey, the first paper we go through is levelized cost of energy-oriented modular string inverter design optimization for PV generation system using geometric programming, which is published in 2022. The advantages of the paper are as follow: a clean and green energy source is used, free raw materials, versatile, significant impact on smart energy network, reduce cost, maintenance is low. But this paper have their drawbacks too. That are it is less reliable power source, and additional investment is done in that. Coming up to the next paper, which is multi-level transformer-less photovoltaic inverter-based real and reactive power injection for single-phase system, which is published in 2020. Transformer-less inverter adopt switch mode technique to convert from DC to high-frequency AC, back to DC and final standard frequency AC, making the circuit board more much complex. Transformer-based inverters that synchronize battery DC with AC output. Coming up to the next paper, which is modeling of power inverter used in PV system, which is published in 2017. Compared to conventional inverter, transformerless inverter are more compact and less expensive. As a result of its one of a kind circuit architecture, it is able to perform the duties of pickup boost inverter without the need for a DC-DC converter bridge. Coming up to the next, which is simulation study of small isolated power electronics converter for PV system, which is published in 2016. There are three main types of PV system that can be designed and simulated. The most prominent feature of PV system is that the ability to quick design a PV power system and estimate hourly, monthly, and yearly energy production number. It was not possible to do shading analysis Design of beneficial PV module modulated on single axis trackers is also a challenge being faced by designers. Coming up to the next paper, which is Design a Single Stage Inverter for Photovoltaic System Application, which is published in 2013. The paper states the controlling of real and reactive power flow is possible, less expensive to purchase, versatile, and can be transmitted long distance over two wires. The drawbacks that is that the inverter has to run at full output in order to maintain its change and may suffer from overheating. If there is not enough sun available, inverter run at full output even if there is no current coming in, potential causing damage to the appliances. Problem statement and objectives. So here is the problem statement, and we come up with the objectives, I mean their solutions as our objectives. So going through our first problem, which is why is the efficiency needed in an inverter? How can inverter be made cost efficient? Can this inverter be used for power the load? Is it fulfilling the growing demand for energy? So we come up, seeing all then considering all this problem statement, we came up with the objective to create an inverter that is powered by solar panel and can be supplied standalone, alerting alternating current load. Conversion of DC to AC electricity will be happening in this. Maximizing of energy production will take place. Effective monitoring of electricity output will be seen in the last. Now coming up to the methodology. So this is the block down we have came through. So here is the PV power system at the beginning of the diagram. Uh, so PV power panel is nothing, it's a photovoltaic panel which will provide DC current to our system. And here is the single phase voltage source inverter which will convert our DC to AC, which will convert our current into DC to AC. And here is the RL load. So in last, to get a desired output, we are using this filter, RL filter. So this is RL load is here, and in last we'll be having the AC grid. So in single phase voltage source inverter, the driver circuit will be connected, uh, giving PWM pulse of 15 volts, and with driver circuit is connected through this PWM generator, which will be having a microcontroller named DSPIC 30 F2010 controller, which will be having input DC voltage of 5 volt. So this block diagram will be more clear in our circuit diagram. So we'll go through that. So here is our circuit diagram. Here is the each section, like SPWM inverter, LC filter, and digital based implementation. So coming up to the SPWM inverter, here is our voltage source, and here is our four MOSFETs. These are actually MOSFETs, and these MOSFETs are connected in H bridge. Like we call it H bridge because it have a structure like H. These MOSFETs are placed at each corner of the edge, and in the middle, our load will be connected. So here we have freewheeling diodes also, which prevent reverse flow of current. Reverse flow of current. So the MOSFET used in this is in channel MOSFET. So this MOSFET now coming up to the like LC filter, here will be having inductors and a capacitor, which will be which will use to filter out the uh, which will be used for filtering, and will after filtering will get our before that we'll be having a pulsating AC, and after that we'll be having a pulsating pure AC using the this load resistance. So in the digital based implementation, we'll be having a proposed technique and SPWM generator from where sinusoidal pulse with modulation will be generating. And then next will be a gate driver circuit, which will be like triggering our MOSFETs T1, T2, T3, and T4. Now coming up to the implementation, the main component of above block diagram is as follows. Solar panel will be there, inverter will be there, driver circuit will be there, SPWM wave generator will be there, RA load, input DC voltage will be there. According to the block diagram, the main controller is PWM generator, which is powered by DC source. It generate UL's with modulated wave as feed the same as input to the driver circuit. The inverter module that is placed in H-bridge circuit takes the input from the panel and driver circuit as produce the output from different cycle accordingly. So here will come with the simulation model. Here is two solar panel is connected on which sunlight, when sunlight will fall, it will take the irradiance and temperature measure it will measure the temperature and irradiance and then convert it in DC power, and there will be a capacitor which will store the energy, because throughout the day we won't get the same current, same DC power. So because sun won't be same throughout the day, sunlight won't be same throughout the day. Morning will be having less, afternoon it will be high, and in evening it will be less. So capacitor is used to get a constant current, and then it will go to our MOSFET, which is MOS1, MOS2, MOS3, and MOS4. And here is D1, D2, D3, and D4 is connected, which is freewheeling diode, which will prevent the reverse flow of the current. And then coming up to the next, there is an inductor, and then our grid. So, yeah. And this is the simulation output. There will be DC voltage and demanded AC RMS current, AC voltage, and AC current will be getting. Coming up to the hardware and software used, hardware component which is used is solar panel, driver circuit, MOSFET, DSP controller, SPWM wave generator, diode, DC voltage regulator, and jumper wires. And in software, we have gone through MATLAB Simulink, MPLab, and PicFlash. So MPLab and PicFlash are used for our DSP controller. To write an embedded program, we used MPLab, and to dump the program, we used PicFlash. Now coming up to the specification of our solar panel, MOSFET and driver circuit components is in solar panel, P max, power max will be 215 watt, and MPP will be 39.8 volts, and IMPP will be 5.40 ampere. VOC will be 48.3 volt, and ISC is equal to 5.80 ampere. Coming up to our MOSFET, VDS will be voltage from drain to source will be 500 volt. Voltage from gate to source will be positive and negative 20 volts, and ID equals to 80 ampere at 25 degrees Celsius. Coming up to our driver circuit, IC used is TLP 250. 250, and resistor will be used. Different resistors are used and diode are used in it. Now coming up to our project setup. So here is the solar panel. Here is our driver circuit, and this is our PWM generator. This is our H-bridge inverter, and here we have two transformers. This is a step-down transformer, and this is tapping transformer. So this step-down transformer will be connected to our 220 volt AC current, which is like our home which is used in our home appliances. So this will be connected to step down transformer. That 220 volts will be converting it to 12 volts and going through this rectifier, which will convert AC into DC. And so there will be pulsating DC. So this capacitor is used to convert it into a pure DC. And then that here you can using CRO we can see check that we'll be getting a DC, which is pure DC, and then DC will go through this MOSFETs, and after that this inverter, and after that it will be converting into AC. This is the inductor, which is which will stop DC and let AC go, and here will be, this is the cap, after that capacitor is used, which will let the capacitor is used. So this will our LC filter. So here we can see our what is that, pulsating AC. So to convert that, we'll be having a RL load, and after using that, we'll be getting a pure AC here. And using this controller, we'll be getting will be like triggering this. Will be giving PWM waves to the our invert this MOSFETs. So it will trigger the MOSFET, and so MOSFET will be the open circuit and closed circuit. Like one first MOSFET and fourth MOSFET will be working together in the half cycle, and second MOSFET and third MOSFET will be working together in the half cycle. So this all is programmed in our microcontroller, and this tapping transformer will be connected to our driver circuit as well as the controller circuit. Now this is the hardware output. So this is the DC waveform which we get from this side. We can, after the conversion, we can verify from this side. We'll get the DC voltage, and AC waveform with distortion we got this side. Like I said, after using LC circuit, we'll be getting this distorted AC. Little bit distortion will be there, which can be uh, purified by using a load. This is our pulsating waveform, which we get at the inverter. So coming up to the application and advantages of project, in applications, inverter are mainly used to converts in a solar energy system. The DC electricity, which is what a solar panel generates, is converted into AC electricity. Inverter are used as emergency backup when there is a power outage. Stores excess power in the battery. Coming up to the advantages, inverter maximize energy production, monitor system output, communicates with the utility grid, and detect faults that might otherwise damage solar panel power system. Cost effective and low maintenance, energy independence. High static gain. A system with high static gain can provide great amount of energy output. A system with low THD produce a clean, stable electrical output that is less likely to cause interface with other electronics device or equipment. So, scope for the future work is, however, the further research should be carried out. It will be necessary, in particular, in order to determine the functionality of circuit relations to the applications of semiconductor device that use silicon carbide. Technologies can work at high frequency with very high efficiency, leading to decline in dimension of passive component, recording load, cost, and space. Future work is aimed to design a hardware prototype of the small scale single phase PV inverter with galvanic isolation, implementation, calculation of efficiency in inverter hardware model as the simulation model. Selective harmonic migration elimination is possible in the proposed inverter by adding up order of harmonic parameter in the controller. Band reject filter can be made use reduce the high harmonic component in the output circuit. So conclusion is, with the scope of this project, the SPWM inverter that is connected to the grid for PV system has been suggested. Conversion of AC to DC happened, and PMW method have been applied, and resulting strain on voltage and current have been studied. The result of the experiment demonstrated that suggest inverter deliver the predicted capabilities. So these are the project list of project publication. We have submitted our project as a paper of 14th ICCNT 2023 conference organization by IIT Delhi conference. And the second paper we have submitted in IIHC conference 2023 organized by Sri Venkateswara College of Engineering, Bangalore. These are the reference we have gone through. These are the papers which we have gone through for our model. Thank you.